Hello everyone, welcome to the third lecture of week 11. So we had been discussing about various architectural variations in the modern LLMs. Now in this particular lecture we will talk about one particular variation while focusing on positional embeddings. So these will be the topics that will be covered in this lecture. We will motivate this from the perspective of long sequence modeling. That will be the focus for the next lecture, but we will talk about that from the perspective of positional embeddings. So we will see certain variations of positional embeddings, specifically how do you learn, how do you put attention with learnable and non-learnable biases. So we will talk about say T5 bias and ALIBI, that has been one of the very popular positional embedding method. Then we will talk about the rotatory position embeddings, the rope method, and we will come back to positional interpolation for rope for modeling long sequences. So that will be the content for this lecture. So I will start with this motivation, that is what we will end with, that how do we do long sequence modeling in specifically from the perspective of positional embedding. See, what is the idea? So typically when we train, we put certain restriction on the length of the input, right, so that we do not have excessive computational cost. But what happens, suppose, see, remember we talked about sinusoidal embeddings, we also talked about learnable embeddings. So if I do this, if I put some length restriction on the sequences during training, and I am using a learnable embeddings, right. So what will happen? So I will only learn up to a certain position, say 1024, but I cannot extend it beyond that position because I have not learned that during training, right. So they have obvious drawbacks, because you do not have embeddings for the position that are beyond the ones that are trained. So that is why either you can use an embedding that is not learned, or we have to find some way in which we can modify or we can reuse this learned embeddings to longer sequences also. So there are two options for this. One is you can extrapolate, that is of course you have learned a function to fit data points within a specific range, but then you can use the same function to estimate the values outside that range, that is extrapolation, or you can do interpolation. So what is the idea? So you have learned it for a certain range, but you have a data into larger range. So what you will do, you will take that larger amount data and put it on the lower range on which you have learned it, right, and you can interpolate. So you map a larger range of data points into the observed range, right. So that is, and this is more preferred, interpolation is typically more preferred, and we will see how we will use interpolation with say rope embeddings towards the end. And this is some visualization of the same thing. So here, suppose you have done no generalization, that is you have learned it up to sequence length 1024, you have these values at different positions, but you do not know what to do beyond 1024, right. So you do not know this. So one thing is you can do extrapolation. If your function is known, you can extrapolate, okay, if this is my function, I can use it for other positions also, right. So like the sinusoidal things, you can extrapolate, right, for the positions, or you can interpolate. So if you have a longer range, what you can do, you can map it to the observed range. So map 2048 to 1024, right, and then you have values for all the positions, right, that you wanted. So of course this position here after this mapping corresponds to 2048, right. So this is the interpolation idea. So now let us go and discuss in detail different sort of attention frameworks apart from what we have already talked about. So one is attention with learnable biases. So remember, this is the formulation we talked about. Embedding at ith position is the word embedding plus the positional embeddings, right. So what happens here, for each token you have independently taken the positional embedding, and you do not worry about the distance between the tokens, right. So what we can do, our positional embeddings can itself take into account the distance between the tokens for which. So, suppose the jth token in the sequence is attending to the ith token in the sequence. So, the positional embedding can actually depend on the distance between the two tokens, right. So, that can be one idea, that can I use self attention with relative positional embeddings rather than having an absolute position for that word. Because what matters is that how long before was that word in the sequence to which I am attending to, right, compared to say another kth word. So, the relative position is what matters. So, how can we put that? An idea is that, okay, why do we need to have separate thing? Why can't I put it inside my self attention equation itself? So, that is, so suppose I am putting an attention from the ith word to all the words before in the sequence in the decoder perspective, let us say. So, what I will do, I will have for the jth word qi kj transpose plus the positional embedding between I and j, right, and divide by square root 2 and any mask thing, right. And now this positional embedding I j can be interpreted as a distance penalty. So, that is if j is much before I, right, too far, then you should have a penalty for that. So, as I moves away from j, the value of p e I j should decrease, right. If it is close, p e I j should be higher. So, that is the idea. So, the first paper like that used that and was popular is the T5 bias paper. In the T5 paper, they use the T5 bias as the positional embeddings, right. So, and they also call it so T5 bias. So, how does that work? Let us take a pair. So, you have the query qi and the key kj, at the position I and j respectively, and you have the offset between them. So, I minus j. So, they said you can use the positional embeddings depending on this offset, right. So, I minus j. So, let us say we call it so for I j. So, I is my query and j is my key. So, positional embedding will be some u I minus j, where u I minus j is a learnable variable corresponding to the offset, right. So, that is an idea, that is, rather than having learnable embedding absolute for the absolute positions, I can have learnable embeddings for the distance between tokens, right. So, but the problem is that if we assign a unique value per offset, I'll get into the same kind of problem that I had with the other embeddings, because I will not be able to use it for longer offsets, right. So, than what I have seen in the training, right. So, when it is larger than the maximum training offset, I cannot generalize it. So, that is why T5 had an interesting idea. So, what you can do, you can group the offsets into buckets, right, and you can have a bucket for everything beyond a certain offset that you have seen, right. So, that was the idea that they used, that they group these offsets into buckets, each will be a learnable parameter. So, I will have some fixed number of learnable parameters, and I will be able to account for any distance that even I have not seen in the training data. So, how does that work? So, they will have an hyperparameter NB, right. So, let us say I fix NB. So, what they will say, so initially I need different bucket for different position, at least for some position. So, they say, okay, for 0 to NB plus 2 plus 1 by 2 minus 1, right, each bucket will have one offset. So, you will have a bucket for offset 0, offset 1, offset 2 up to certain thing, right. So, you have some buckets that are there for some small offset. After that, each bucket will have more offsets. So, how do they do that? So, they say, okay, let us say I have a max distance. So, I will say log of max distance minus log of NB plus 1 by 2, and then for the current offset I will have log of I minus j minus log of NB plus 1 by 2. So, here I minus j is less than equal to dist max, maximum distance, right. Let us say you have some maximum distance from the training, and you are saying, okay, so beyond NB plus 1 by 2 minus 1, right. So, I mean beyond this up to dist max, use this formulation. So, you will keep on growing the bucket size, right. So, they will increase logarithmically. Now, what will happen if I minus j goes beyond dist max? So, then they said, okay, you just create another last bucket, and everything else that is beyond dist max you put in the last bucket, right. So, all the offsets that are not assigned to previous buckets will be in the bucket NB. So, how many buckets will be there starting from 0 up to NB? So, there will be NB plus 1 buckets, and that many learnable parameters you will have. You will learn that many parameters. So, if you want to visualize this, what is happening? So, this is for n b equal to 32. So, there will be 33 buckets. So, bucket 0 to bucket 32, right. So, there are bucket 0 to bucket 32, there are 33 buckets, and for roughly half of them, so 0 to 15, there is one bucket per offset, right. So, offset 15, you are in bucket 15. So, that takes care of the offset that will matter in the nearby context, but then you will grow them exponentially. So, they will grow them. So, in some logarithmic way. So, you have 16 to 20 all have the same bucket 16, 21, 26 have the same bucket and so on. 802 to everything else beyond it has the same bucket, right. So, this was for a dist max of 1024, and that was the idea. By that, you are ensuring that you have a good distinction in the initial half, right, but later on also you are able to account for any distance, and there is some logical way of extending it, right. So, the last bucket contains all the query key offset that are not covered by the previous buckets. So, T5 bias is a popular module that can be used for extending beyond whatever we have seen in the training, because you learn these embeddings and you can apply to any length, any offset in the inference time. So, together this is how it will look like bi minus j. So, this is the function q I k j transpose plus u b I minus j, right. So, I minus j is the offset, and this is a learnable parameter. So, you learn that during training. How many things? Only n b plus 1 things. So, n b plus 1 things are learned, right. And how do you get this value? So, they say okay, which of these bucket it will correspond to is what I need to know, and this is a simple mapping. So, somewhere it is the same offset, otherwise logarithmically, right. So, you learn these parameters and you can use that during inference also. Now, this was the one with the learnable biasage. Can we also have attention with non-learnable biasage? So, that is why we will talk about this very interesting approach, attention with linear biasage, right. So, what we can do, we can give biasage fixed values via certain heuristics rather than having them trained, right. So, idea will be then they will not be dependent on the training data set. You can just like sinusoidal embeddings, they are not dependent on the training data set. You can just apply it on any new data set, right. And once you have set the particular way of fixing this. So, what does this approach do? Attention with linear biasage, ALIBI approach. So, very similar idea. So, bias term is defined as a negative scaled query key offset. So, you have I minus j. So, P e I j is minus beta times I minus j, right. I is here and j is here. So, you can say beta times j minus I, right. So, that means as j keeps on moving away from I, you keep on having a penalty, right. So, fixed penalty now to q I k j transpose, and of course, this will be a negative thing always, right, because j is before I in the sequence. So, you are adding a negative quantity to this. Now, what is this beta? So, they have a scalar. They said okay, you can either fix it or you can even tune in a validation data set. So, this paper for example said that it is better that you fix beta, and what they found out works is they have a factor 1 by 2 to the power a, and because you are using multi-head attention, you can set a separately for different heads. So, they said okay, you can set 1 upon 2 to the power 8 by k. So, for the multi-head attention, so this is for the kth head, right. So, this is so for each head you will have a separate value for beta, right. So, separate value of beta for each head, and this is the formulation. So, you can order them in some way, first head, second head, third head up to whatever, and this is what you will use. So, this is the ALIBI approach that so there you can just take the offset between I and j and you can apply this with this beta parameter, right, and this will give you the attention. Now comes the most recent and most popular embedding method, that is rotatory positional embeddings. So, they have a very different concept about positional embedding. So, till now, so we saw that you can either use some hard coded values, right, that was one of the best sinusoidal for all dimensions, but they are additive. So, you have the original embedding xi and you add a positional embedding at the ith position. So, you have this as the embedding. So, rotatory positional embedding say okay, what you can do, so you can model this positions as rotations, right. So, you have an initial token embedding, right, but rather than adding some position, you rotate it for a various position. So, that is, if I put a token at different position, I just rotate it, right. So, this means you will multiply it by some matrix, and that is where you get the new embedding to work with, and these rotations will capture the positions, right. So, what is their idea? So, let us say xi is my d dimension embedding. So, the rotation will be again d cross d dimension matrix that represents what are the rotations you need to perform on the token embeddings. So, to understand this idea, let us take a very simple case. Let us say we have 2 dimension embedding, right. So, that means the rotation will be a 2 cross 2 matrix. So, I start with x1 x2 and I apply a rotation by an angle theta. So, what is the corresponding rotation matrix? So, this will be this matrix, right, for multiplying with an angle theta. So, cos theta sin theta minus sin theta cos theta, right. So, that means if I start with x1 x2 as my initial embedding, after rotation this will be my embedding cos theta x1 minus sin theta x2 the first dimension, and sin theta x1 plus cos theta x2 is the second dimension, right. Why does that make sense? So, let us take an example. So, we are taking a vector say xy, right. So, let us say I am here. So, and this is, let us say its length is r and angle is phi to start with, and this is my x. So, this is my x and this is y, right. So, initial vector is x y. Now, I rotate it with theta, right. So, I rotate with theta angle again. What will be this new value, right. So, initially what is x? X is nothing but, if this length is r, x is r cos theta cos phi, angle was phi, and y is r sin phi, right. So, x is r cos phi and y is r sin phi. Now, let me apply this rotation matrix to this. So, cos theta sin theta minus sin theta cos theta to x y. What will I get? X cos theta minus y sin theta, x sin theta plus y cos theta, right. That is what we got. Now, let us put x as r cos phi and y as r sin phi. This is what I will get, x as r cos phi and y as r sin phi. So, we can put r as common because this is common across all. So, r and then this formulation. What are these? This is cos of phi plus theta and this is sin of phi plus theta. So, that means now this vector is, its length remains the same, it is still r, but so these are r cos theta plus phi and r sin theta plus phi, right. So, this is all modeled through this rotation matrix. So, now the angle is theta plus phi, that is what we wanted, right. So, this particular thing makes sense, that if I had some initial x1 x2, I can rotate by through this rotation matrix and it will take into account the angle, right. The magnitude will remain the same, only it will be rotated, right. So, it does not change the magnitude, just rotates it by an angle, right. So, now see, what is important is that we will say whenever we move one position, we do one rotation by theta. So, what if I move by some t positions, I positions, I will do a rotation by t theta or I theta, right. So, if I rotate by an angle theta for t times, right. So, it is like t theta, rotation by t theta. So, I can say simply I multiply by rotation matrix for t theta and I will get cos t theta x1 minus sin t theta x2 first dimension, sin t theta x1 plus cos t theta x2 second dimension, right. And this t you can interpret it as the position of a token that is denoted by x in the sequence. So, what will happen? So, you think about the position 0. In the position 0, the rotation is also by angle 0. So, you retain the x1 x2 in the position 0. But when you move to position 1, you will do a rotation by, or you can call it x r theta, right, position 1. In position 2, you will do x r 2 theta, and like if you go to position I, you will do x r I theta. So, same word with this embedding x, depending on what position it is in the sentence, in the sequence, you will give its embedding in incorporating the position embedding x r I theta, right. So, and as we said, rotations do not change the magnitude of the embedding, only they incorporate the positional embedding, the position information through the rotation, because you keep on having the angle multiplied by the number of positions, right, in the sequence. Okay. So let us try to make sense of that. So, that means suppose I have a vector x, and if I move one position, I will multiply, I will rotate it by angle theta, this will be x r theta, but if I move it by 3 position, I will do rotation by 3 theta, and I will get this x r 3 theta. Okay. Now, why is that a good way of modeling the positions? See, remember what we are interested in, the relative positions. So, what if I have two sentences, let us say there are two sentences, and I focus on the word. So, the cat is sleeping, so cat and sleeping. So, cat is the second position here and sleeping is fourth position here. Now, take another sentence, every afternoon you will find that the cat is sleeping. Now, cat is 9th position, sleeping is 11th position. So, does that preserve the distance between cat and sleeping in both the cases? Let us see. See what will happen here. So, I will have cat rotated by an angle of 2 theta and sleeping by some 4 theta, right. So, to get here, and I will have some angle between them. Yeah, let us say in this case this was cat 2, this was sleeping 4, and there is some angle. If I go from this sentence to this sentence, do I still have the same angle between these two embeddings? So, what will happen now? So, cat 2 to cat 9, I will do a rotation by 7 theta. So, I get somewhere here, even sleeping I will rotate by 7 theta. So, the inherent angle between cat and sleeping will remain the same, even if the absolute positions are different. So, here what is happening, absolute positions are different, but the relative positions are same. And in that case, the similarity between the embeddings, that means the angle between the embeddings, that remains constant even if you move the absolute position, and that is what it is able to capture, the rotational embeddings, right. Now, so this is about 2 dimension, but we have seen we will have some d dimension embedding, say 300 dimension or 500 dimension embedding, right. So, how do I extend it to any d dimension? An idea is very simple, you have something for 2 dimension, you need one angle for 2 dimension. So, every 2 dimension you need another angle, right. So, if you are having a 512 dimension embedding, you need 256 angles, right. So, I have d dimension vector, I will have, you see, theta 1, theta 2, theta d by 2, you need d by 2 angles, right, where each of this rotation matrix is 2 cross 2 matrix. So, it is not a fully diagonal thing. So, you have a 2 cross 2 matrix here, another 2 cross 2 matrix here, and again with the 2 cross 2 matrix here, right. So, you have only say 2D non-zero entries in this d by 2 cross d square by d square matrix, only 2D entries are non-zero, others are 0, right. And where each you can see that each rotation matrix is 2 cross 2, right. And there are d by 2 parameters, d by 2 thetas that are controlling these angles of rotation, and theta k is set to a very similar value as you did for sinusoidal embedding. So, this is 10,000 to the power minus 2 k minus 1 by d, you see, and k will go from say 1. So, you will have minus 2 0 by d to d by 2. So, minus 2 d by 2 minus 1 by d. So, that is how this will vary, and you have a base that is 10,000 to the power. So, that is how the thetas are set. So, and very similar to what we did in the sinusoidal embedding. So, now this becomes a bit cumbersome. So, rather than doing that, we can have a very simple way of solving it. So, you see, if you have two dimension, you have x1 cos t theta k minus x2 sin t theta k in the first dimension, and x1 sin t theta k plus x2 cos theta k in the second dimension. So, how we can represent that? We can say, okay, so we can have x1 times cos t theta 1 and x2 times cos t theta 1, right. Yeah. So, in the second dimension, yeah. So, you can separate out the terms for cos t theta and sin t theta. In the first dimension, the only thing was cos t theta 1. In the second dimension, again cos t theta 1 for x 2. What happens in the sin t theta? X 2 times minus sin t theta in the first dimension, you see. So, we have swapped it, minus x 2 times sin t theta 1. Second dimension, x 1 times sin t theta 1. Yeah. So, this becomes an easier way of doing this. So, x 1 x 2 up to x t, but here you do certain changes. So, minus x 2 x 1 minus x 4 x 3 minus x t and x t minus 1, and this you multiply by sin t theta 1 sin t theta 1 sin t theta 2 sin t theta 2 and so on, right. So, this becomes an easier way of implementation, right. And once you have it, I mean this is for t theta, for any ith position you will simply rotate by xi I theta. So, you have the xi here, right, and you will put the particular I here for the ith position, and you get your final embedding output for any I and the d dimension embedding. So, that is how the rotatory embeddings, positional embeddings, the rope works. Now, the thing we talked about, see even here we are saying we have a fixed set of thetas, right. So, what if I want to extend it? So, we have we are right now this is going up to only d by 2, right, and only d by 2, they are only d by 2 angles. So, you can only go up to d by 2, right. What if I want to extend it beyond d by 2? So, given this background about rotatory position embeddings, let us see how do we really implement it, right. What are all the parameters that are there, and how does it really work. So, let us see suppose I have a token at the mth position and I want to apply rotatory position embedding to that. So, interestingly it is applied only when you compute the query and key embeddings. Okay. So, let us say I have a function. So, this is my embedding for the word at the mth position, the normal word embedding. So, this is the normal word embedding, and m is the position, and this means I can use this formula for either query or key. Same formula would work for both. So, let us say I want to apply for query, right, the query. What will I do? So, I will take the embedding, and like I used to do, I will multiply with the WQ, right. Now, this would have a separate dimension than what I had in the original word embeddings. Like for example, so this is for the Llama 7 billion model. So, it has D model is 4096, but it has 32 attention heads. So, what is the dimension of the query or key? D model divided by n head, that is 128. So, my effective D for which I will apply rotatory position embedding is 128. That is the dimension of key and dimension of query. That is very important. That means I do not need to apply it for the entire D model dimension embedding, but only for after I have projected it to the query and key individually. Now, I will apply this matrix, and as we already saw before, this will be the matrix. So, what is interesting here? This is for D dimension, right. So, and this is a D cross D matrix, right. I want a final D dimension output. So, D cross D matrix multiplied to some D dimension output, where we know a block of 2 cross 2, 2 cross 2 are there. So, how many different angles are there? So, if you see there are angles for position m, there are m theta 1 to m theta d by 2. So, there are only d by 2 base angles, and then you multiply by m is the position. So, you multiply by m theta 1 up to m theta d by 2. So, for position m, for position 1 you will just multiply by theta 1 to theta d by 2, right. So, m is just the position. What are theta 1 to theta d by 2, what are these? So, they are also very standard, fixed values. So, any theta I is a base value b, that is same as sinusoidal 10,000 to the power minus 2 I minus 1 by d, and I belongs to 1 to d by 2, right. So, for I is equal to 1, this will be 10,000 to the power 0, right, and for I is equal to say d by 2, it will be minus 2 d by 2 minus 1 by d, right. So, it will go from 10,000 to the power 0 to 10,000 to the power minus 2 d by 2 minus 1 to divided by d, right. So, these are also fixed. So, you have fixed theta i's, the base thetas, and you multiply by m for the position. So, m theta i's, right? And you have d by 2 such things. So you will only have d by 2 such different angles that will multiply for every position, and these angles will change depending on positions, right, because of this m multiplication by m to these thetas. The base thetas remain the same, but this m changes with each position, and the same m is applied to each angle, right. So then effectively I do this multiply with this rotatory embedding for position m. Say suppose my query is at m and key is at m. So this will be my query embedding. Finally, I will multiply the embedding with the query matrix and then the rotation, transpose, and then similarly for the key embedding, key matrix, and then the rotatory for position m, right. Take a transpose. So if you take a transpose, what will happen? X. So this will be xm transpose wq, then r theta and minus 1 wk. So this is like you are doing this and this. So this will be r theta and minus m, two matrices together, then wk and xm. So this is how you have the effective multiplication. So this changes, right. Earlier it was just wq and wk. Now you have an additional rotatory thing that is coming in between, right. So that's how you apply it. Now we can also visualize this once. So this is for 2-dimension case. So let's say my query key are 2-dimension. So remember, for every 2-dimension we have one angle, right. So if we have d dimension, we have d by 2 angle. So for 2-dimension we have only one angle, theta 1, that is constant. Now depending on the position, right. So if I am at position m, so for this word I'll take the original embedding, the query embedding, and do rotate by m theta 1, right. Same for key. So this will be the position encoded query key, where I take the original embedding, multiply by wq or wk, and then I do the rotation, right. So this is the process, and that's why rotation needs only d by 2 angles, where d is not the model dimension, d is the dimension of the query or key, right. Now this is for extending it to many dimensions. So here you have 6 positions, and you have the sentence and hence transformer with rotatory position embedding. So for every 2-dimension you have one angle, right. So 2-dimension theta 1, next to theta 2, and last to theta d by 2. You have d by 2 such angles. For position 1 you will multiply with theta 1, theta 2 up to theta d by 2, right, the embeddings. Position 2 you will multiply by 2 theta 1, 2 theta 2, 2 theta d by 2, and position 6, 6 theta 1, 6 theta 2 up to 6 theta d by 2, right. So this is what will change. These thetas remain the same, but how much do you rotate by, this changes based on the position, okay, right. Now we started with lecture by saying that we will do extension of the context window by 2 methods we can do, either extrapolate or interpolate. So this particular paper actually saw what happens if you extrapolate versus interpolate for this rotatory position embeddings. So this is some sort of attention score, like before taking softmax. They had certain theoretical values, so based on which they plotted. Then they say, okay, this is in some range, right. So this looks like okay range, but they trended for 2048. This was for llama 2, 2048 sequence length they trended, but then they tried to extrapolate for length beyond it. And what they found, that in this range this behaves nicely, but when you extrapolate, this does not behave nicely, and you see this goes to a very high value, right, and that this will cause some huge issue in the attention computation, and that's what they found. So as soon as they increase the context length, I mean, there is something that goes wrong, because what is happening? So you have trained it for certain length only, up to certain angle only. So you have trained it up to say m theta, right. So m theta 1 up to m theta d by 2, and this m is fixed during training. So let's say m is 2048, you can go up to 2048, theta 1 to theta d by 2. So you know how to work with those, but whenever you go beyond, say m is equal to 34443, and then you have to multiply, rotate by 3443 theta 5 or something, right, immediately there is some problem, right. And they have certain theoretical analysis on why this may happen, right. But then they say, okay, what if I don't do extrapolation, but I do interpolation, right, and then they found there is a nice stability if you interpolate, That means you somehow convince the model I am still in the same range, right. How do you do interpolation? It is not very difficult, right. So, they do something called position interpolation, they also known as PI, position interpolation, and very simple idea. So, let us say I have trained it for understanding from sequence range from 0 to L. So, let us say L is 2048. Now, at inference time or some other time, so you have maximum position is somewhat higher. So, you want to go for L prime is equal to 4096. You want to extend to this length or say 20,000, 30,000, right. So, what is the idea? Idea is that I want to represent the positions in this new range such that it still fits this, right. And how did they do this? They say I don't want to extend the angle that I have shown them in the training, right. So, what is the maximum angle I had shown them? Say 2048, in this case 48, right, was the maximum angle that I had shown them. So, now suppose my L prime is 4096. So, 2048 times say theta 1, let us say, and similarly we will have the theta d by 2, right, up to 2048 theta d by 2. So, what I will do to fit a larger possible length is say okay, I will interpolate it to the same range of up to 2048. How? So, suppose this was my model. So, that was applying to x and m position earlier, this was my model f x m, right, f x m, where this was my rotary matrix with m theta 1 to m theta d by 2. Now, the new angles will be, so originally they were m theta 1 to m theta d by 2. What will be the new angle? So, I will say okay, it will be m L by L prime theta 1 to m L by L prime theta d by 2. Okay. So, if you see in this particular case L by L prime is roughly half. So, that means you are reducing the rotation by half, right, so that it can fit. So, you are just changing your rotation. So, you are saying okay, I will rotate by half. So, it will be m theta 1 by 2 and up to m theta d by 2 by 2, right. That will be the rotations, new rotations. So, you change the rotations, right. So, if the sequence level increases by twice, you change your rotation, you divide by rotation by 2. So, and what they said is that okay, in this paper what they have shown is that, so once you do that, it is better if you further do a little bit fine tuning, so that the model learns how to work with this slightly different notation. So, we can further fine tune this model using the next token prediction task, and with this interpolated position encoding on the extended context window, and they can say you can use very small data, say thousands of sentences will be sufficient, so that it actually interpolates. So, this is the position interpolation, that is okay, if I want to use larger length, I can just use this particular thing. So, effectively this will reduce the angles, right, by m L divided by L prime. So, L by L prime is the effective or L prime by L is the effective increase that you want in your context window. So, you accordingly decrease your angles. Now, there is another paper, so this effective long scale context modeling of foundation models, where they said okay, so this is one method rho PI, so position interpolation, but you can also do, you can also have another way of changing the same thing, and this is what they call as ABF, adjusted base frequency, right. So, this was based on their experiment that they found. So, they did a very simple task that they will give very large input, and they will ask the model to retrieve the first sentence, that is what they will train it for. And they found that beyond 4000 to 6000 tokens, the model was not able to attend effectively even after using this positional interpolation. So, it could interpolate up to say 6000, but not beyond that. So, they say okay, can I have another modification? So, they said right, what is the other way I can modify, right. So, if you see your actual formulation of, so you have so we have two things here, right. So, we have this base to the power something and we are multiplying it by position m. So, m and this b minus 2 I minus 1 by d by 2, right, by d. yeah, I minus 1 by d by 2, so I minus 1 by d. So that was the formulation, right, and this b was 10,000. Now, so one way I can reduce the angle is by changing m. So I can change m to m l by l prime, that was pi. Another is I change the base itself, right, that will also reduce the effective rotation. So this adjusted base frequency is what changes this 10,000 to something like a large value 50,000. This 500,000 is what they used. So they changed this base from 10,000 to 500,000. You can actually derive a formulation on how to change it based on the new length, but they did this particular change, and this actually reduces the rotation for each dimension. And they say by doing that, it was much more effective to train with or do inference over long context models. And this is a picture where they are showing for rope model in blue. So if you increase the distance between querying key tokens, what is the attention before softmax? And you see it reduces drastically in the case of rope, right? As you increase the difference, it is better in rope pi. You see this, the yellow curve is better, but it's much better in rope ABF, the green curve. This is the best curve, right? So it does not decrease like drastically. So it has some value. Now they also compared another method that we are not covering, this XPOS method, adjusted base frequency, but rope ABF seemed to be the best, right? And they also saw what is the validation perplexity if you train with this rope ABF method. So it was better than both rope and rope pi, right, for all three data set that they considered. So this is another method that you can use, the rope method, and you can either change the effective angle directly through m, or you can change the base frequency. So there are two ways that people have tried: pi changing effective m, and ABF changing this p. Okay, so this is, I mean, this lecture we devoted completely to position embeddings and how to use them for long context modeling. And this foundation of large language model will be a reference for this. And the next lecture we will continue our discussion on the long context modeling, right, through other methods. Thank you.